You can watch an aircraft receive fuel from the terminal window. A hose connects, numbers climb, and minutes later, the airplane leaves. It looks like a delivery. But that hose is only the final visible link in a chain that began far beyond the airport. Behind the wing sits a fuel farm. Behind that may be a pipeline, road tanker, rail car, barge, ship, or several of them in sequence. The system is built to maintain flow, even though control changes hands at every transfer point. That creates a strange possibility. An airport can have fuel in storage and still struggle to deliver it at the moment an aircraft needs it. To understand why, we have to follow one load of jet fuel backward, then run the entire system forward. Our journey begins at a refinery where crude oil is separated and processed into products with different physical properties and uses. Jet fuel is not simply anything that burns. It must leave production able to meet a demanding specification throughout the journey ahead. Aircraft cross hot ramps and extremely cold air at altitude. The fuel therefore belongs inside a defined performance envelope. Quality assurance is not a final inspection at the aircraft. It is a condition the product must preserve as it moves between facilities. Once released into distribution, a batch becomes both material and information. The liquid moves through hardware, while records identify what it is, where it came from, and which transfers it has passed. Physical flow and documented identity travel together. There is no universal route to an airport. Geography decides what is possible. Scale decides what is economical. A coastal hub may combine ships and pipelines. An inland airport may depend on rail, road, or a long pipeline shared with other demand. Intermediate storage acts like a timing buffer. Large shipments can arrive in pulses, while the airport consumes fuel continuously. Tanks between those rhythms let the upstream network receive in one pattern and feed the airport in another, reducing exposure to an interrupted route. Every transfer changes more than location. It can change the operator, measurement point, schedule, equipment, and responsibility for the batch. The fuel must remain usable through all of those boundaries. A handoff is therefore both a movement and a test of coordination. Before fuel reaches the airport fence, the system has already performed its first invisible task, converting irregular production and transport into a dependable arrival stream. The airport does not control the whole route, but its operation depends on what that route can deliver next. That is the first principle of the journey. Movement is useful only when identity and quality survive it. Distance alone does not bring fuel closer to a flight. Every kilometer must end in a handoff the next operator can accept and continue. Near the edge of a large airport is a place most passengers never notice, the fuel farm. It may contain receipt equipment, tanks, pumps, filters, control systems, and loading positions. This is where an external supply chain becomes an airport operation. Arrival does not mean immediate availability. The receiving process has to confirm the product, the transfer path, and the conditions under which it can enter storage. The airport boundary is not an open pipe. It is a controlled interface with operating procedures. Some airports receive most of their fuel through pipelines. Others rely heavily on trucks, and some retain trucks as an alternative when a primary route is constrained. Each option carries a different relationship between shipment size, arrival frequency, road access, and transfer speed. Inside the farm, the total shown on a tank chart is not always the amount operators can use immediately. Fuel may be arriving, settling, being checked, reserved, or positioned in another tank. Inventory is a number. Availability is a state. The size of a fuel farm reflects more than today's departures. Designers consider how reliable the upstream chain is, how many flights operate, which aircraft use the airport, and how demand may grow. Storage is partly a response to uncertainty outside the fence. From the control room, the farm is read as a moving system. Operators need to know which tank is receiving, which path is isolated, where flow is headed, and what demand is approaching. The important picture is not volume alone, but configuration over time. A larger tank can give operators more time to respond to an upstream interruption. It cannot make a blocked receipt line move, complete an inspection, or place a dispenser beneath a wing. Storage protects the operation, but only the connected system can deliver. Now look inside the pipes. The product appears uniform, but its usefulness depends on what has not entered it, what equipment has touched it, and whether every transfer followed the correct path. A small process error can change the status of a large volume. Contamination control follows the fuel because exposure follows the fuel. Storage, handling, and distribution all create points that must be managed. Water and particles are not cinematic threats. They are operational reasons for sampling, filtration, drainage, inspection, and disciplined equipment use. Quality is protected through layers rather than one magical test. Product verification, equipment checks, records, access control, and trained handling reduce the chance that the wrong material or an unsafe condition travels farther into the system. The system is industrial, but it is not autonomous. People accept deliveries, identify products, connect equipment, inspect vehicles, respond to spills, and stop a transfer when conditions are wrong. Training is part of the infrastructure because hardware still depends on correct decisions. Before flow begins near an aircraft or service vehicle, procedures address ignition sources and static electricity. Bonding is one example. Create the intended electrical connection first, then transfer. The visible action is small because the hazard it manages should remain invisible. Filters, hoses, nozzles, tanks, and hydrant components are not separate props. They form the physical route. Each item adds useful control, but also another inspection and maintenance obligation. Reliability comes from managing the chain as connected equipment. When a check raises a question, operators do not gain time by pretending the fuel is available. The responsible action may be to isolate a tank or pause a transfer. That protects safety, but it also removes capacity from the schedule until the issue is resolved. This is also why compatibility matters for new fuel pathways. A certified drop-in blend is designed to work with existing aircraft and distribution infrastructure after blending. Without compatibility, airports would face separate handling systems and many more opportunities for confusion. At this point, the airport owns or manages inventory that has survived several controls, yet the passenger's aircraft still has none of it. The system must now convert stored volume into precisely timed flow across an active apron. Only after the product and route are available can dispatch solve the final distance. The question changes from whether the airport possesses fuel to which aircraft needs it, which path can serve that stand, and how the transfer fits the turnaround clock. At a large gate, a compact hydrant dispenser may arrive beside the aircraft. It looks like a fuel truck, but it may carry little or no delivery inventory. Its job is to connect the aircraft to fuel moving through pipes beneath the apron. A hydrant system shifts transportation below ground. Pumps send fuel through a network that reaches selected gates. A dispenser connects a hydrant pit to the aircraft, controls the transfer, and provides the final filtering and measurement functions required by the operation. At another airport or another part of the same airport, a refueler truck may carry the product itself. The truck loads at a facility, drives to the stand, transfers fuel, and returns. That route is flexible, but vehicle capacity and travel become part of timing. Hydrant systems and refueler fleets solve different versions of the same problem. One invests in fixed distribution and short final connections. The other brings mobile storage to the aircraft. Neither is automatically right for every scale, layout, or traffic pattern. The final transfer begins with an instruction, not a guess. Fueling personnel must connect the correct aircraft, product, amount, and distribution request. This is where operational data meets physical equipment. A precise order turns inventory into the load needed for a specific flight. Fueling does not own the gate. It shares a narrow window with baggage loading, catering, cleaning, boarding, and technical work. The safest path through that space depends on coordination, equipment placement, and rules for what can happen at the same time. Completion is another handoff. Flow stops, delivered quantity is recorded, equipment is disconnected and secured, and the area must be ready for the next movement. The system has not finished when the tank is full. It finishes when the aircraft can safely continue. What looked like a simple hose connection is the endpoint of production, transport, storage, quality control, dispatch, driving, and gate coordination. By the time fuel reaches the wing, most of the work that made the transfer possible has already happened elsewhere. Here's the bottleneck promised at the beginning. It is not necessarily an empty tank. It is the slowest safe handoff at the exact moment. Demand peaks, a receipt lane, a quality hold, a pump path, a vehicle, or an aircraft service position. Inventory answers, how much is here? Throughput answers, how much can move correctly in the available time? Those numbers can tell very different stories. A full facility upstream of one constrained path can still produce a queue downstream. Average demand can hide the hardest minutes. Flight schedules often create waves of work with several aircraft needing service in overlapping windows. The system must survive peaks, not merely satisfy a daily total. Timing converts demand into a capacity problem. Tank capacity also has configuration. One vessel may be receiving, another may be held for checks, and another may be feeding outbound operations. The total volume across all three can overstate what the farm can deliver right now. Redundant routes are valuable, but they are not always equal. Trucks may preserve supply when a pipeline is interrupted, yet road capacity, loading positions, travel time, and unloading rate determine how much of the original flow they can replace. Quality control can become the deliberate bottleneck. If product status is uncertain, stopping its progress is the feature, not the failure. The operational challenge is having enough alternate capacity and schedule margin to protect both quality and continuity. In a truck-served operation, the limiting resource may move around the airport. A vehicle is unavailable while loading, driving, servicing, or returning. Dispatchers are effectively solving a live routing problem in which every assignment changes what can happen next. This is the answer to the opening puzzle. An airport may possess fuel yet lose time because stored volume and deliverable flow are different products. The practical capacity of the system is set by the handoff that cannot safely move any faster. Now let one handoff lose time. Not a disaster, just a blocked route, a late truck, an inspection, or unavailable equipment. The aircraft remains safe at the gate, but the schedule margin surrounding its turnaround begins to disappear. The delay first appears in fuel dispatch. Then it reaches the service window. If other turnaround tasks cannot absorb it, departure readiness moves later. A local constraint becomes visible only after it travels through several linked decisions. Operators have recovery tools. They can reroute supply, change tank configuration, dispatch a different vehicle, resequence work, or use inventory accumulated earlier. Resilience is not the absence of disruption. It is the ability to preserve service while conditions change. Redundancy gives the system choices, but every choice has a capacity. A second route matters only if it can be activated, supplied, staffed, and connected in time. A backup on a diagram becomes resilience only when the operation can actually use it. Information shortens the distance between a problem and a response. Industry disruption alerts, local inventory status, demand forecasts, and equipment reports help operators decide before the passenger sees an effect. Visibility is another form of usable capacity. The exact map changes by location. Local rules differ. Small airports may use simpler systems. Large hubs may centralize storage and distribute through hydrant networks. Ownership and access models vary too. The mechanism is shared. The architecture is not universal. One late service does not automatically collapse an airport. The effect depends on available buffers and recovery choices. But aircraft, gates, and crews continue into later assignments. That is how a modest local delay can become part of a larger operational pattern. Passengers experience this network as a time on a screen. They do not see the rerouted truck, isolated tank, or dispatch decision that protected the flight. The system becomes visible mainly when its margin has already been consumed. We began at the wing and traveled backward. Now run the system forward. A specification leaves production. Transport modes carry it toward the airport. Intermediate storage smooths arrivals. Receipt controls admit it into a new operating environment. Inside the fuel farm, tanks buy time while checks protect product integrity. Operators configure routes and match available inventory to demand. Pumps, filters, vehicles, and records convert stored fuel into a controlled outbound service. At the final handoff, a hydrant dispenser or refueler connects that service to one aircraft. The fuel crosses the last hose, but the journey succeeds because every earlier interface delivered the correct product with enough time remaining. The real system is not a row of tanks. It is the synchronization of quality, capacity, routes, equipment, people, information, and time. Remove one layer, and inventory can remain physically present while operational availability shrinks. The next time you see a hose beneath an aircraft wing, you are looking at the last 10 meters of a journey that may span hundreds or thousands. The visible product is a flight, but the hidden product is synchronized fuel logistics.